Triangle Man. Triangle Man hates Particle Man. They have a fight. Triangle wins. Triangle Man.
Essentially, this whole thing is going to be, you're wondering why we're doing proofs. We are going to prove triangles congruent. That is ultimately the goal of this entire unit, to get us going and make sure we understand triangles. So we have different types of triangles. Remember, acute were all angles less than 90. So if you have an acute something like this, all the angles are less than 90. Something where all angles less than 90. How about obtuse? Well, you've got one that is bigger than 90. Ooh, these are rough drawings. So you've got this one angle that makes it obtuse. Hope all those are less than 90. How about a right angle? Sure, or a right triangle. It's just a triangle that has a right angle in it. Awesome. So our angles, we just made triangles out of them. How about scalene? Scalene means that none of the sides are the same. So like if I do something like this side does not match this side, which does not match this side. That is a scalene triangle. No sides are the same. This is the one we're going to look at a lot, is the isosceles. What does that mean? It means two sides are the same. That's an isosceles triangle, and that we'll come back to. Equilateral, all sides the same. Da, 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 da. Everyone matches. So you can have an all match, two match, or no match. And then in this isosceles, it's so important. We have some stuff here. The side that doesn't match is called the base. It's the base of the triangle. So when we look at this, if this is the base, we have what's called base angles. And yeah, I would jot all this down. This is a base angle here, and here are base angles. So what's the other point? If the bottom is the base, what's the top called? It's called the vertex. So we also have the vertex angle. It's this angle right here on top. Excellent. Very good. So we're going to need that coming up, actually, I think right here. So a theorem we need for this one, for our proofs, is going to be the isosceles triangle theorem. So if two sides of a triangle are congruent, then what happens? Then the opposite angles are congruent. Using my best handwriting here. Opposite angles are congruent. I'm going to abbreviate a little bit here and use this for congruent. That's perfectly legit. So let's draw a picture of this. What is going on here? So if you have essentially an isosceles triangle, that's what it's saying, two sides are congruent, what must be true? So if I've got A, B, and C, so if I know that AB is congruent to what, BC, what has to happen? If I draw my picture again over here, what's going to happen? Here's my A, B, and C. Let's change colors here, make it a little more dramatic. If those sides are congruent, these are the opposite. So opposite would be like, here's this side, opposite is this one, opposite of this one is this one. So if these sides are congruent, the base angles are congruent. Pretty cool. How about the other way around? Can we do it the other way around? If two angles of a triangle are congruent, then what? Then the opposite, what do you think here? Sides. The opposite sides are congruent. So this is just saying we can go the other way. So if you have a triangle, let's call this one DEF. So if we give you angle D is congruent to angle F, then what has to happen here? If this is congruent to this, what's the magic here that happens? If I know D is congruent to F, if I know this is going on, then I know the opposite side. So where are the opposite sides? This one is congruent to this one. So it's like the same thing backwards. Converse, remember, that's why we're switching them in chapter 2. It's just switching around. I switch the definition around. So either way, if you ever see these two angles, mark the sides congruent. If you ever see these two sides, mark the angles congruent. Excellent. So can we do that with some numbers here? Let's try it. I love these. So here we go. So I see, oh, these two angles are congruent. So it's isosceles, and that means this is equal to this. Well, if this is equal to this is also x. So can I solve for x? Sure. I know that what? Triangles all add up to 180. That's key. Triangles add up to 180 degrees. So I know that 48 plus x plus 2x's is got to be 180. And then can I solve this bad boy? Sure. Just subtract 48 from both sides. We got 2x equals, what is that, 132. Divide both sides by 2. We're looking at, is that 66? I hope I did that right. So this is going to be 66 and 66. So double check it. Let's take a look at the next example here. So we got another isosceles triangle. So this time I give you the sides are congruent. If this side is 2x plus 3 and you meant to fill this in, and this side's 4x minus 7, well, if they're congruent, they equal each other. So hopefully We did a lot of this back in chapter 1 and whatnot, and in chapter 3 came up setting things equal to each other. So set it up, they equal each other because it's isosceles, they're congruent. And then let's just go through and solve it real quick. Get all your x's on one side. We're looking at 2x minus 7 equals 3. Then get x by itself, so we'll add 7 to both sides. Fantastic. So solve some equations. We're looking at what? X equals 5. Fantastic. Let's up the ante here a little bit. Let's check out this example. This time is a little different. I got x squared plus 3x. This side equals 40, so don't freak out here. Same thing. Go ahead and set up your equation. We know that x squared plus 3x equals 40. So can we solve this? So maybe it's been a while since we've solved one of these things. When we have this x squared in here, we want to set it equal to 0. So what we're really going to do is say, okay, let's subtract 40 from both sides. So we've got a quadratic. When we have a quadratic, we're going to set it equal to 0. So we're looking at x squared plus 3x minus 40 equals 0. Now, once we have that, the reason we do that is now we're going to try to factor it. So when it's set equal to 0, we're factoring it. I like to make this little magic x over here. We're looking for numbers that multiply to negative 40 and add or subtract to the middle number, which is 3. So you kind of have to go through and say, okay, 2 times 20 is 40, 4 times 10, all these different combinations. Which one add or subtract? I think we're going to use 5 and 8. 5 times 8 is 40, and then if I subtract them, 8 minus 5 is 3. So who has to be negative? For negative 40, this guy does. Negative 5 times 8 is negative 40, 8 minus 5 is 3, or negative 5 plus 8 is 3. So what does this mean? This breaks down into x minus 5 times x plus 8. So we factor that. Why do we factor that? Well, we're going to have it equal to 0. This is one parentheses times another. So if you can make this first parentheses 0, 0 times anything is 0. If you make the second parentheses 0, 0 times anything is 0. So it's a great way to solve these things. So let's solve it. So I'm really looking at when is x minus 5 equal to 0. And the other thing I want to look at, when is x plus 8 equal to 0. And so what do you have to do to solve them? No problem, just add 5 to both sides for this one. So we're looking at if x is 5 is one possible solution. What's the other one? If you subtract 8 from both sides, we're looking at if x equals negative 8. So notice we have two answers now. That's cool. That's how it's going to be. We're looking at this. We have x squared. It could be x is 5 and x is negative 8. Two solutions for that one. Awesome. On here next. So same thing we did with the isosceles triangle theorem. We're going to need that. What about equilateral? So think about a triangle as equilateral. So I'm talking about all the sides are the same. So here it is. Here's an equilateral triangle. If a triangle is equilateral, then what has to be true? Then it is what we call equal angular. Kind of a weird word. A lot of vowels lined up in a row right there. Equal angular. So what does that mean? If this is true, then what has to be true about ABC? Man, these are some sharp looking triangles here. If it's all the sides are the same, what do we know? All the angles are the same. So if I give you all the sides are the same, all the angles are the same. How about the converse of that? Can we flip it? If a triangle is equiangular, then it is what? It is equilateral. So the equal just means equal, equilateral. So if I give you a triangle where all the angles are the same, what has to be true? On DEF. So we've got all the angles are the same. So then we're looking at all the sides must be the same as well. Pretty cool. So I know it kind of makes sense once you see it, but we may need both of these for our proofs coming up, which I'm pretty fired up about. Alright, so let's take a look at two more definitions that are hugely important. We're going to do proofs, so we need to know this stuff. It's kind of a bit tedious now, but it's really, really important. Get us going for proofs coming up this chapter. So what are congruent figures? To be a congruent figure, you have to be exactly, that's the key word, exactly the same shape. And not only the same shape, you have to be exactly the same size. That means congruent. Same shape, same size. Woo, that's rough looking. Let's try that again. Same shape, same size. That has to be exact. So we're not going to just say, okay, these two sides are congruent or these two angles are congruent. We're going to say these shapes are, these triangles, these polygons, these whatever. We're going to show that all kinds of shapes are congruent. So what's important about that? Well, we have to know corresponding parts. To show this, we're going to say, okay, some parts match up. So these are like the sides or the segments. So these are like the sides and angles that match. So if you are congruent, you're going to have parts that match up. If two things are congruent, they're going to match. So those are called corresponding parts. Let's take a look at some of this. Can we do an example of this? Sure. So if I check this out, so this is really important how we name things now. So I'm going to say triangle EFG right here is congruent to ZXY. So they're congruent. They're exactly the same shape, exactly the same size. We may flip it, we may turn it, we may slide it, we may move it, we may rotate it, we may do all kinds of stuff, but we're not going to change the shape or the size. So how do I know who matches what? If they've got these corresponding parts, who matches what? Well, it tells you E matches Z, F matches X, and G matches Y. So without a picture, I know right off the bat, if they're congruent, angle E must be congruent to what? Just by the way it's worded, angle E must match angle Z. That is true. These are corresponding parts, E and Z. So I can mark it. This is congruent to this. So you can tell I definitely flipped and turned this one right off the bat, make it tricky. What else matches up then? Well, I know angle F has to match what? Angle F has to match angle X. They're the same. They're the second one in the order. So F matches this one. I'm going to give it 2 slices. Matches X. And then you can tell what's left over. G's got to match it. And it is a third one. G matches Y. So G matches Y. 1, 2, 3. Awesome. So those are the corresponding angles right there. If it asks you to list all the corresponding angles or something like that, you can list them. What else do I know has to be true? Well, I have to know from E to F, check this out, it's got to be from Z to X. So E to F matches Z to X. So they're congruent, and it makes sense. These two angles are the same with the side in the middle. Then I'll go F to G. F to G is going to be what? It's the last 2 letters, so that'll be X to Y. And then what's left over, this is the weird one. G to E matches Y to Z. So it kind of goes back to the beginning. These 3 matches 3. So I'm going to have you mark these, list these, make sure that you know the corresponding parts of these. So again, if you had to list these out, you could write, EF is congruent to XZ. And we can list all the corresponding sides. Awesome. Okay, example 2. So I give you a picture of 2 congruent triangles. We're supposed to name the order of these. So triangle, let's just name the first one however you want. I'll go RQS. You can name it however you want, in any order. But if I name it RQS, now it's really important how I name the second triangle. It has to match. I like looking at the angles. Angle R matches what? Matches angle B, so B must be first. They're a match. They're corresponding angles. Then I went RQ, so it has this one segment right here. Which way do I go with the B? Do I go BD or BC? I go to the one with the 1 here, so that'll be BC. And then what's left? D. So, oops, not B. How about D as in dog? All right, let's try that. BCD. So, do they all match up? Is R to B? Yes. Q should match C, Q matches C, and S matches D, and all my sides in between match up. You could list all the corresponding parts from this if you wanted to, and have them all right. Okay, so with that in mind, let's finish this up. So we know corresponding parts. So I'm going to give you these triangles are congruent. Let's go ahead and find, really I'm only asking you to find this, but I may go ahead and mark the whole picture just to make sure we're good. You need to find who matches SR. So I'm looking for who matches SR. If you look up here, we can start naming it. I know RT matches TR. It better because it's the same line, isn't it? RT and TR. Awesome. And I know TS matches... TS is the last 2, matches RG. So they're matched. So who's left over? Aha. I know SR must match TG. So these segments are corresponding right here. They're the corresponding segments. If you want to do the angles, you can go ahead and fill in all your angles. You can say, oh yeah, R's got to match T. Let's see. So R matches T. T matches R. This is kind of cool in the other one. We're doing this. And then S and G got to match up. Woo, pretty crazy. A lot of little slashes on there. Awesome. How about the next one? You can draw a picture if you wanted this, but you don't really have to draw the picture. I know ZX would match ZX. That's kind of weird. They must be sharing it. XY matches XG, and here it is. YZ matches JZ. So YZ matches JZ, and I'm good to go. Awesome. And then the finale here, I just put touching together. I mean, sometimes they have a point common. I'm looking for an angle, M and L. So I'm looking at M to N to L. So really important how we name angles and whatnot. Who does this one match? Again, I may have flipped it, turned it, done something to it. So let's start marking it. I know L matches what? I. Ooh, it definitely flipped on us. Or I mean turned on us. M matches 1, 2, 3. H So that leaves n matches n. So it is the same angle on both sides. So to name this, you could name it INH or HNI, doesn't really matter. Anyways, good. Excellent. Very nice. Good work on this. Good luck on the practice and on the mastery check. I hope it goes well. Peace out.
Particle man, doing the things a particle can. What's he like? It's not important. Particle man, is he a dot or is he a speck? When he's underwater, does he get wet or does the water get him instead? Nobody knows. Particle man. Triangle man, triangle man, triangle man hates particle man. They have a fight, triangle wins, triangle man. Universe man, size of the entire universe man, usually kind to smaller man. Universe man, he's got a watch with a minute hand, millennium hand, and a neon hand. And when they meet, it's a happy land. Powerful man, universe man. Person man, hit on the head with a frying pan, lives his life in a garbage can. Person man, is he depressed or is he a mess? Does he feel totally worthless? Who came up with person man? Degraded man, person